Okay.
It's my pleasure to introduce Mingze today, who will tell us about flag varieties and convolution algebra structure and the cohomologies.
Does this only record one board or?
I can
Okay.
use the camera, but
I mean, it's fine. I can also use.
yeah, but it's better to use like two boards on the left and
Yeah,
on the right.
sure. Okay, so, right. Let's just get started. I guess it's a bit unorganized, but I don't know where I would introduce a new section, but that's for the sake of having some organization. So we start with varieties. Well, I guess okay, so let's take some semi-simple reductive, whatever, group G. Throughout the talk, it's probably good to just keep in mind that, for example, like SLN. And in some of my proof, I'll kind of just only do it for SLN, but it should work for everything. Over C, of course. And take the standard Borel, just upper triangulars. Diagonal. Right. Then we have this projective variety, G mod B, which is isomorphic to just complete flags. Or you can also think of this as Borel subgroups. Or sorry, Borel subalgebras. But I guess today the perspective is probably think it this way. I mean, this is just because G acts on flags on the left, and the stabilizer of the standard flag is just B. Right. So sort of the goal is understand the T equivariant cohomology of this flag variety. And sort of by what's the topic called? Induction or whatever. This is the G equivariant cohomology of G mod E times G, or G acts diagonal. And I guess this is because I don't know, I will draw a little. I mean, do I need to write this out? No, I'll just write this out. This is because this is just the same as of E cross E final product. Same as here, you can cancel the G's. And B retract to T, so. Yeah. Anyway, so and the reason why we kind of want this is because from Oison's talk last time, this thing has a convolution product on it. So you can sort of describe the algebra structure. Describe this thing as some algebra geometrically. I guess last time we really talked about Borel more. Convolution product, but only thing you need is to do the construction completely the same way. Well, I guess you did with sheaf, but as long as you have those pullback along smooth maps and push forward along proper maps, you can define the convolution the same way as from last talk. I mean, in this case, everything is fine. Since G mod B is yeah, so okay, so the first thing, whenever you see something like this, a good question to ask is what are the T stabilizers, the T fixed points of this thing. So here T just acts on the left. And by some kind of localization argument, if you know the T stabilizers, you can understand this cohomology thing. So I don't know if I should. Yeah, I'll just write it down here. This is isomorphic to the Weil group. Explicitly, this thing is equal to just let's call it PW. You just pick any representative of elements of the Weil group and the cosets. Right.
We did not discuss optimization, but I guess it should be fine.
Yeah. I'm just saying sort of this is general strategy, right? I mean, I don't need to say it, but this is just, yeah. I guess it's like, why do we care about this thing at all? Right. Well, I mean, one reason. And it's funny, I was trying to figure out how to prove this, and I asked the AI to prove it, and it did. It took 2 tries, so at least, did it slightly wrong the first time. The same mistake as I did. But right, I guess, I mean, the proof is you literally just write everything down. Sort of if you just have maybe I don't know, AI proof.
Standard proof.
Standard proof. Yeah, standard proof. Yeah.
Just written somewhere.
Yeah, exactly. But it's not trivial. Yeah, you kind of have to think about it a little bit. At least for me. So maybe I'm not good at group theory. So right, so we want, let's say P, so just take some GB in this thing, right? In the flag variety, and then you want this to be equal to GB. So we basically have okay, just GB equal B. I'm not gonna write the over B thing. So this is just saying this is another maximal torus contained in the Borel. Right. So by I don't know what the theorem is called, but this thing is going to be the conjugate of the standard Borel by some elements in B. B T B. Then you just have B G inverse T G B inverse equal P. So this thing is something of B. And in particular, G is in WB. So you get something WB, and you can see that this only, once you quotient out by T, this is like unique. Yeah, but I guess the way, the geometric reason sort of, let's say geometric or the human proof, I don't know. T acts on flags, you're just scaling everything, right? The T action is just the diagonal matrices. No, I'm not sure if this varies. Yeah, it made sense when I wrote this down, but I don't remember.
I think you just look at the smallest subspace, which is not spanned by this basis elements, and get a contradiction immediately. Get that it's not a T-fixed point.
Anyway, maybe I'll just leave the AI proof because the human reason is not working. It made sense when I wrote this down. Wait. Yes, okay, sorry. Now it makes sense. I don't know, human. But it's kind of a sketch. Reasoning rather than so I think the T, if you pick some flag, you have some filtration, then the T are just gonna scale the each basis elements, right? And then all the flags that are going to be fixed with a relative, all the flags that are going to be fixed are just going to be all the flags that are also permuted by each basis element. But you can reorder the basis. Yeah. Basically. T action flags are this is require you to sort of write down the flag in the specific. You write down a matrix or whatever, and then you pick some basis write down matrices, and then T are just gonna scale the diagonal, and all the other flag all the flags that are going to be fixed by this are you're just reordering the basis. Yeah. Fine. Well, I guess, yeah, in the GON case, then the reordering is corresponding to the while group elements.
Yes. So if I'm looking at SL2, G mod B is P1. Right?
So there should be two orbit.
And then so the T action is just times 0 infinity, and then the T action is just moving and everything. Yeah.
Yes.
And then 0 and infinity with infinity.
Okay, so next thing is right from Buha decomposition. You can write down so you get some sort of all these sets are going to be isomorphic as sets. You have the wild group, and you have p orbits. Let's say the normal one. So just G, the set of double cosets, or I mean, this is just rewriting the definition. P orbits in G mod B, and G orbits in this product, where it acts diagonally. Here it acts by left, or yeah, here left. So I think the easiest way to think of Bruhat decomposition is from the last perspective. So it's basically by using a G, you can move the first one to like a standard reference flag, whatever. So this is just tells you that W just parameterize a pair of flag in whatever the W picks out a relative position. Should I make this more explicit, or people want to move on? Huh? Good. There's sort of an algorithm you can write down for this. It's really explicit. Okay, so now I have another board, right?
Yeah, I think there is also a cheating proof where you use this.
Yeah, I guess I can also use this space.
T action to prove that T. So there is this theorem, the Beninsky-Brewer, that
Right.
G mod B is a union of its attractors with respect to
Right. Yes.
vectors, and then you prove that these attractors are precisely the orbits.
Yeah.
And
Yeah.
gives you W.
Yes. I guess that's like the proof in Chris Ginsburg.
Yeah.
Okay, so right, so let's use, since we're doing flag variety, let's use this thing. This thing. So let's write down from this third thing. G mod B is going to be union of the B orbits of those T fixed points. W, so W and W, well, you pick some representative of B. Yeah, so this is coset. It's cosets. And I'm going to cut, and these are the goes this way. Schubert cells. So I probably did not spend enough time to try to understand what these Schubert cell looks like. But I can write down for you, at least in the case of general for SLN. Give me a flag, or like which flag are in which Schubert cells. So SLN, let's take some permutation. Then the condition that a flag V is in the Schubert cell is condition that if and only if intersection with the first, so I'm gonna use FJ as the standard flag. F is gonna be the standard flag. I have enough space. Okay. Okay. Boy. Right, so this is prescribe you the relative position with respect to the standard flag.
Shouldn't it correspond to matrices somehow, like basic
Yeah,
matrices?
I mean, you can write down, I mean, because you have I, J, and K, you can roll this. Like, let's do an example. Let's say 2, 3, 1. This transposition in let's take G equals to SL3 and the omega equals to 2, 3, 1. Or 1, 2, 3, I guess. Yeah, it's the same thing. Yeah. Then you can just record this in a tablet or a matrix or whatever. I, J, 1, 2, 3, 1, 2, 3. So for I equal 1, you're looking at the number of Ks that are less than 1, such that WK is less than 1. Well, but 1 maps to 2, so there's 0. Yeah. And then you just fill it in. I think it should be something like this. 2, 1, 2, 3. Well, the last one is always going to be 1, 2, 3. Yeah. This should be correct.
Sorry, what do these numbers mean?
These numbers are K. So in the table, this is K. So the condition is the dimension of your I filtration with the first J standard coordinates subspace is equal to how many number gets moved in front of J. Yeah.
Yeah,
Like how many J you need.
in elements of SLN are matrices and I think you can write.
Oh yeah, you can also
you can write like with pivots and whatever. Like you use right B to do Gauss elimination, and the result of Gauss elimination and factorial ways for a pivot like this
yeah
wants to appear.
Yeah, you can also do it that way. But I guess here, like, I guess the nice thing is you don't need to choose a matrix to represent the flag, but
Yeah.
Yeah.
Is the little circle?
These are open because these are open. So, right, I will write down what these things are. Isomorph. I mean, the shoot G mod B. Wait.
Not necessarily close.
Not necessarily close. Yes. Not necessarily closed. Yeah.
So for G equals SL2, what is this decomposition? So I should get two pieces. Just point and either.
Yeah, point and everything else. Yeah. Yeah, I think
it's upper triangular and directions.
Yeah.
No.
Yeah, and I think the open part is like you require these things to not be equal to 0 or something.
Yeah, maybe upper, maybe lower. It's similar. It's easy.
Yeah. Okay. Hey. Oh, I have another board here. I forgot.
Maybe it's not a no.
Oh wait. Oh, I just.
Yeah, it's a good idea if people see everything. No,
Okay.
just
Okay. Right. I think this should be translated to, if you want to write this v down more explicitly, should be, so the first line says, you pick the first filtration, v1 should be, it's not in e1, and it's in the span of e1 and e2, right? So this is going to be, v1 is going to be something like lambda e1, where plus, sorry, should be e1 plus lambda e2, where this is not zero, right? If lambda is equal to 0, then it's going to be 1. And inside v2, so the first one is this. And then the second one should be, what did we say? I guess there's no condition on the second one, since when you intersect, it's in the span of. No, so it's going to be e1 plus lambda e3, right? Yeah. Sorry, yeah, some other thing. I have difficult picking another. Okay. Use all of these. And if you take the closure, then you just allow these to be equal to 0. Right? I think I did this correctly. Is this true? V2. Yeah, because this says V2 when you intersect, like if there's an E2, then this thing will be like 2 here. Okay, so right. This thing is going to be sort of from Burha decomposition is going to be so R minus meaning the negative roots. So U beta just means the unipotent corresponding to the beta weight space. Yeah. And this is equal to just, no, we'll just write C to the length. Length of, yeah, because the length is exactly how many roots gets reflected from the negative plus to the positive. So in particular, the dimension of this cell is, well, the real dimension is 2 times this. Why is it C to the? Because each piece is one-dimensional. So this is the weight space in the adjoint representation corresponding to beta.
U beta is a line.
Yeah. Yeah, it's a copy of C. Okay, so now. Ooh, this is bad notation. What's a good, I guess E could be for, no, E is for 5. I want to use F for like the filtration, but I will use F for the standard flag, so. Huh?
There we go.
Curly F, okay. Thanks for the suggestion. So let's define F. P is just some number, I guess. This could be the union of all these Schubert cells with length less than P. And if I don't write this, means it's the closure. Okay, yeah, these. Then from the Brouillard decomposition, you get the filtration. F0. It's all the way to the top one. F. Oh, I see. Weird. There we go. Dimension of. Now, I guess we didn't. Okay, so the point is Fi minus Fi minus 1 are just are affine, some affine space. Just C to some n. Huh? Oh, yeah, should be union of what did I write here? I did not write down whatever. It's then some copy of that stuff. It doesn't really matter because we just need to use this as some union of affine things.
Yeah, but maybe it's I just because of what you wrote.
You just the largest.
Like the difference is the union of open
Yeah.
of open brass.
Union of open Brouillard cell with a fixed length, but there might be there's multiple cell with the same length.
Yeah.
So
Yeah, but the length is P is and this fixed length. So it's the length is the same, so N is I because the dimension of open brass cell with double double is I is I. So there is no need to an I.
oh, just I.
Yeah, it's just more
Okay. Union. You're correct. Well, maybe 2I, but whatever. Oh, it's C, so it's just I. Yeah. Okay. Some copy of C to I. Okay, so in this situation, and also these things are B equal B closed, B equivariant,
invariant.
B invariant, yes, B invariant. Sub varieties. So, in this situation, there's this situation. We have cellular equivariant, cellular fibration, cellular decomposition. Decomposition. There. That tells you that. So first of all, each of these subvariety will represent has a fundamental class. The equivariant subvariety has fundamental class. You can think of taking the Poincare dual of the Brown-Moore represented by these subvarieties. So E it's this. And it's same, this is also T invariant, so you can replace. If you erase T or T.
Is it being explained of the fundamental class or the number class of the points?
Oh, yeah, it's the invariant class. I mean, it's just the class represented by obviously. Maybe I should write it below. Maybe like that one. Yeah, everything is good.
I mean, the kind of didn't discuss it, but we discussed only usual fundamental classes in variable cohomology, but
Right. You take the thing, you take the normal product with e.g.
no, you should use approximation spaces. You can use e.g. only for vector bundles, but for fundamental classes you could use approximation spaces to e.g. but when you're fine. And
right.
I mean, we did discuss it, and it's not too bad. It's a more technical point.
So these Schubert cells give you basis. Right. So the next thing is sort of there are geometric way to understand this cohomology better because there are parabolic version of all these things we talked before, and sort of having these parabolic things that allow you to do some kind of induction thing. Yeah. Parabolics. So in general, if I have a subset of the simple root, I get a parabolic Pj, which B union U, I guess, negative alpha, where alpha is in this, or in J. Yeah. So for example, the minimal you can do just adding one, right? So for example, you can just do in the SLN, do you take, let's say just the first, I don't know, first root or whatever. Yeah, let's say SL3. I forgot how to label
The product.
Huh?
I think it should be product.
Oh yeah, sorry. well, let's say just the group generated by these things. And yeah, so wait, if I want to just add this block, which group should I add? I don't remember. So I mean, you have the B, and then you can have like 2 by 2 block here, basically. Yeah, if you're adding one root, I don't know.
Well, the first one.
The first one, yeah, sure. Yeah. Okay, and then. Right, so this also give you a while loop, which is just subgroup generated by, I don't know, S alpha, where alpha is in J. And we're gonna use this other thing. You take W mod WP. Right. Okay, yeah, so I don't know, plane proposition or whatever. So if I take any coset here as unique representative W min of minimal length. I mean, this is essentially if you change by something WP, you're reflecting some simple thing across some simple thing, then you're gonna increase your length. And W maximal. Okay. My organization is terrible. Okay, so I guess I'll use the notation from there. We can do all the things we did here, but for this parabolic. So you have sort of a Bruhat decomposition where you have G mod P is equal to union W and I forgot if it's in the entire while loop or no, it should be in this. Yeah. Or you just choose some representative for each coset.
This will be.
Oh, yeah, sorry. B, this is P. P will be. Yeah.
Can you talk about the max length? Are there any like further constraints?
No, it's just unique.
What if the P is pretty low?
Oh, we ignore.
No,
Well, I mean, Peter, you have the maximum element of.
Oh.
There's just one element.
Yes.
One element next to it. Is minimal, then perform one reflection, and if you use it, it's
Okay, I see.
minimal flexible.
Okay, so, and right, so the important thing here is just, I should probably write it that way, but I didn't write it down on my notes, so maybe I wrote it over there, but the important thing is the Schubert cells has dimension equal to the length of the minimal representative. So, so I'm gonna call these at W. What did I call, did I give? Oh yeah, so the top ones are these brackets, and these are the square brackets. Yeah. So this is, so these are also affine, because it's just some copy of U. And, right, I should say this is also, you have a T action on here, and these are exactly the T fixed points. So this is just the length of W length. So, we're looking at this map. So we want to use these Schubert cells in the parabolic case to learn something from to do something about the standard the full flag variety. Oh yeah, so these things are like partial G mod P is partial flag variety. So in this case, right, you're just saying that your flag will, let's say P is like the first root, including the first root, then your flag is just going to be, I mean, it's just the Grassmannian of planes in, so in this case, G mod P is just Grassmannian of planes in, wait, is this true? Hold on, wait,
Yeah, I think so.
yeah. You're just missing the first line, yeah.
Yeah.
You don't know what happened to the first line.
Second it would be smiling of lines.
Yeah.
It's in a line. Then we
Right. Okay, so we have this map pi. Maybe I should say pi j when you fix when you fix some j as subset of the simple, and you have reflection. So how do you see G mod B G mod B j. Okay, so we want to look at the push-pull along this map. For the Schubert cells. Right, so from all we talked about before, these Schubert cells will generate the B equivariant cohomology over a point and T equivariant. Okay. So just from this dimension thing, you can actually know a lot for example, pi maps the normal Schubert cell here corresponding to a minimum representative isomorphically to this. Yeah, just literally just from this dimension thing, and then you have containment. Well, I guess it's you only know the open part. Wait, did I? So yeah, when I didn't put, I actually couldn't find anywhere like it maps the open part isomorphically. So I guess it's birational, but I don't know if it also matched the closure to the closure, like 1-to-1 or whatever. I don't think it matters for our situation because you don't really care about the cohomology process anyway. So
It's like open part to the whole time.
so it's open to open, yeah. Open cell here to open cell there. And by the like you can prove one is clearly in the other, and then the dimension is the same. And they're just some AN to it's AN contained in AN. So
If we look at the big open cell, it can't map isomorphically. The big is kind of for the closure. If you look at the big open cell, like the closure can change.
right.
But it's doesn't, but it's not me. It's not minimum. You know, they
Yeah.
minimum elements in the.
Yeah, maybe I'll just say, okay, by this I mean birational, then it's fine. And then you also have, well, I guess I didn't write down the thing for the maximal representative. But yeah, basically it's also the second statement is also a dimension counting thing by sort of looking at the codimension of this map. This is equal to X. There's probably a better way to see this, but I just thought of dimension. Just good enough. Okay. Okay, so from this, what do we know is that I from this. Know that uh, uh, maybe for class, I will just you can do either B or T, doesn't matter. B or T. Let's do T because that's what we want. Let's take the T equivalent, everything do T equivalent. This is just what did I say? Up here. And then try pull back. Oh wait, I forgot to. Oh no, it's fine. I mean, I think it's just because if you have subvariety mapped bidirectionally into the other subvariety, then the push forward of that class would be just equal to that class, right? This is probably some proposition in Anderson-Fulton. I mean, this is the argument they wrote in the book, so this is by property.
I just have to, you just have to follow definitions and apply comparability 2 times, which is
Sure, yeah. Well, I mean, they did everything from equivariant cohomology, right? So yeah. Definitely true in normal topology, so.
Yeah, I guess it's just like the class forward, so first one should be bigger, but the second one is, I guess it's cheaper.
Right, so I guess I should write one more thing here. So from these two, we can define this. Well, maybe I should put J everywhere for this pi just to label it. But just pretend I wrote J everywhere for this pi. So I'm gonna write Vj is equal to pi j. And the only case we really care about is when J is just one simple root, minimal parabolics. Okay, and so these are just inside, and these are all HT point linear maps. So there are some like cohomology operations, basically. And this is an algebra. We took some operators and definition. Where is? Do I have space? I'll just write down. Basically, the nil-Hecke algebra is just the subalgebra of this endomorphism algebra generated by these operators. I think it's enough to take the simple, just the minimal parabolic. Yeah. Definition. nil-Hecke. Algebra of, do they usually label I don't know how they labeled it, like G mod B or nil-Hecke of G? Yeah. Of G, I mean, it just depends on G, right? Or whatever, G mod B or G mod B. It's just, well, I guess you also have to take B, yeah, to choose. Is the subalgebra of this endomorphism, this thing. generated by the digits as above. Yeah. Well, I mean, you actually just need to take the simple reflections and there's some relation.
It generates the same thing as always.
Yeah. Yeah, maybe I should say let's say samples.
This about algebra or H star sequence about algebra.
H star this thing, right? Over H star T point. Yeah. Okay, so now questions?
Maybe you're just gonna say it, but like, curious, when you push your tools, so like, or those basis elements, you know, what the.
Sorry?
Or like those class like, sugar coming in.
Yeah.
Goes.
I did not write down on my notes, but just based on what I wrote down, you can get very easily. It's just switch the min to the max.
Right.
Min to the max and then kill everything else.
Can you write that? Can you like,
I mean, yes, I can.
What I'm trying to ask is like, in the sugar spaces, like, can you say what DJ is food or like.
Yeah, like you mean if you write everything down in polynomials?
You just like as a variables.
I guess it's everything W meant for some like W.
No,
I don't think so.
yeah, that is a estimate.
Yeah, but I don't know.
It's just like matrix of J in terms of the basis of the division or.
I mean, you should be, I think. The push pull has a very, very simple description.
Being correct about describe the JSON.
Yeah. Well, I don't know if I have time to do the algebraic. Yeah, but I'll do, yeah. Okay, so. Now remember at the beginning, oh, I erased the stuff from the beginning, but this thing is also HG star of G mod B cross G mod B, right? So this thing has a convolution algebra structure. And it turns out that these operations are just going to be convolution with certain subsets in this thing. Yeah. Do this. Okay, so now let's just do focus on the SLN case. That's what I did in my notes, not sure why. Okay, and let's just take alpha. It's just equal to some simple reflection, some transposition. Let's see. Then or I mean, you can literally, if you want to keep that example in mind, just 1, 2. So I'm gonna go phi I P. No, P. PI. Or PI is just parabolic with respect to this reflection. And I'm gonna write down OSI equals to G, the G orbit of things in relative position psi. So. Yeah, so this is in. Just. Or I mean, this is a G orbit in the second. Okay, so now. Yes, there. First part. Okay, so. OSI closure. Is just. Equal to. The fiber product. And two. Projection. To both projection to each part. Each factor. Is a P1 bundle.
Projection of the closure.
Yeah, projection of this thing. Or I'm not sure if it's the open one or closed one. Now I think about it.
No, shouldn't be close.
Should be close, yeah.
We can't really CP1 bundle. It's hard to do projects when you're with CP1 bundle over chain or B, then it's projected.
Right, it should be, yeah, I think it's,
complete itself.
yeah. How would I prove this?
So, so like, I
Yeah.
especially, so like, that pattern cloud cover Gmod PI. So then naturally maps to the project without Gmod PI. And
Yeah.
I guess I'm assuming the image is was like bar and then is that
Sorry?
Is that so like that thing mapping to Gmod P times Gmod P is the image was like R and then map is isometric, is that what it's about?
Sorry?
Sorry. Yeah, like Gmod P times Gmod P over Gmod PI map to Gmod P times Gmod P. And then map, what I'm asking is.
Oh, definitely, yeah, that's still pretty good. Yeah.
No, this is just a subset. This is a subset like.
It's just a subset, it's a fiber product.
Pairs, and these are pairs that map to the
Yeah,
same.
this is the fiber product.
Sorry, like you couldn't hear either because.
Oh,
Yeah. This product over something is always a subset in just a product. To take a product over something is a subset where they are to the same thing, so it's a subset in a natural way. And this is description. This subset is not a closure of this.
Okay, let's look at the second one. Yeah, I don't remember how I proved the first one now. It's not even the same. Wait. Oh, no, okay. No. So let's say we're working. Let's just do specific examples. Here. Right, so you can say O as one. Okay, let's take G equal SL3. And let's say I'm just taking 1, 2 as alpha or SI as well. All right. 1, 2. Then your what did I wrote? Wait, this should be in. Oh yeah. So these are. You can think of as you can. I'm just not sure if I'm mobbing out G somewhere. Because I want to say OSI or O12 are just all the flags that are in relative position, like switch the first one. But I'm not sure that's
Relative position is for two flags, but you can fix one flag.
yeah, that's what I'm saying. But so here I need to look at, do I need to mob out G somewhere or?
I mean, it's just convenient to think about it if you like project everything, just to project everything to remote B.
Yeah.
Then this is open Schubert cell, which is just a fine space, A1, and it's closed Schubert cell. D1, which is the union of this open and trivial Schubert cell. And then
Well, yeah, I guess
it was the description is symmetric. And you can kind of see it by hand.
I will write down what I wrote in my notes and see if it makes sense. So I guess what I'm doing is I'm fixing the first one into just the into the standard barrel, into the standard flag. So it should be corresponding to flags that are in relative position. 1, 2 with respect to the standard flag. Right. So these are, what does that mean? Is basically your first vector, the line. So it's going to be set stuff like line generated by right? E1 lambda, no, E1 plus lambda E2 inside E1, E2, I think. Right? These are your flags.
I think actually you should move lambda to the left earlier. So in the example that you raised, and here also is a lambda E1 plus E2.
Lambda.
And
Oh yeah. Wait.
E1 is bad because then it would be in a fetal position, but E2 is fine. It's like, it doesn't matter. So it should be lambda E1 plus E2. Giving you
Lambda.
exactly.
Right. Yes, you will always want some. Yes. Yeah. My mistake. It should be lambda E1. This is what we want.
Minus A1 instead of E1. It's great.
Okay, I mean, this is definitely correct now, but I'm thinking, how do you prove this now? Yeah.
I try to digest from your example and
Mm-hmm.
say it makes sense, like this OSI would be like pairs of flags that differ by SI.
Mm-hmm.
OSI bar is like pairs of flags that either differ by SI or not. Don't differ.
Yes,
Okay,
exactly.
And that's exactly when you map to the same thing in GMO PI. Is what
Yes.
part one is saying, right?
Yes. Right. Actually, that's the proof, I guess. Yeah. So because it's like they're in really exactly. So if you don't take the closure, then you're not gonna have. Well, then it's just the same thing. But the fiber product over PI, that means you're mapping to, so here, right, so here G mod B maps to G mod P1, 2, yes, is you're mapping a flag into just, you forget the first line, right? You ignore the line and then just or you ignore F1, and then you just choose the plane. Right. In the whole thing, right? So you just remember the plane. So now if you think about what the fiber product is, it's just saying I'm choosing a pair of flags that the line can line on whatever in the first plane, right?
Yeah, the plane is the same, but the lines in open.
Yeah, but in the open cell they might be different. In the closed cell they can be the same.
Yes.
And that's exactly what happened, or what the fiber product says. And this also tells you that this is a P1 bundle, because you're just everything over the same fiber is just you choosing a plane. You're choosing a line within the first plane. Yeah. Sorry for the confusion or whatever. Okay. Okay, now we're almost. Okay, so now there So theorem says convolution with this OS. I think I need to put G here. Yeah, so now we consider this is an orbit, so you can consider this as living H, this thing here. This involving with this is the same as the SI, I should write SI, DSI. Right, so I guess the DSI a priori is defined on the T equivariant of G mod B, but you can identify these two things together. Right, so the proof is just looking this, you have this diagram. One. Okay, so now let's see, what does this thing do?
So what is X and that sign?
Why did I write X? Sorry, X, I guess X is G mod B. Yeah. I guess I should just write G mod B everywhere, or is this fine? Okay.
And XI is G mod PI?
Yes, Xi is G mod Pi. G mod P SI. Okay. So let's say I'm going to take some class A. H which one do I do? Confusing myself. Should be on HT. G mod B. Yeah. No, sorry, HG of G mod B. Or HT. Now I'm kind of confused.
The not trigger is T of G mod B or G of G cross B.
Right. So yeah, sorry, it should be this. Because I won't apply this to it. I think I'm doing something wrong. What am I doing wrong? I'm not tracking the groups. But let me just check the notes. Hold on real quick. I'm sorry. Yeah, I think. Wait. In the notes, they also did HG of G mod B. Is that a problem?
I don't understand why that's true.
Well, I mean, I guess the thing is we want to use the, right. We want to use the convolution structure on this.
So then it should be HT of G mod B plus G mod B or HT of G mod B.
Or why is it, why is that? I thought the convolution is just. Okay. Well, let's see. I forgot the groups, so let's carry on this proof without writing down, and then let's see which one is correct. So let's take a class in, here's a great solution, just without writing the equivariant part. Just H of love. So question mark, here we go. Yeah. Or I guess I just wrote X. And then what is this convolution? I'm just going to take P2, pull back of A, and then, oh, I forgot to write down this. Cup product with this fundamental class, but this fundamental class should just be, I will write down the fundamental class, but then we will explain exactly what's happening. Yeah, it's weird because we're looking at fundamental class in the cohomology, but I will write down what is happening. So claim is claim. Well, maybe I just claim it. So the point here is we're going to use the projection formula. Yeah, so the projection formula says that if I do pull back E2 of A, and then I'm going to apply it to a point. The reason is because Poincare dual, if like the point is the fundamental class of this thing, right? With Poincare dual. And then when you push forward to it, and then take the Poincare dual, you get the fundamental class in that thing. Right, so this projection formula just going to give you P2. Wait, P2. Q2. I think I should write Q. Q2.
In the diagram.
Oh yeah, sorry. I should. Here is correct. P2, and this is Q2, right? It's all screwed up. So I guess I'm using. Oh, it's just P. Yeah. By projection formula, this is this. Right? Into intersect or not intersect. Should be dot or this with just push forward. Of this class.
Isn't that just the same, the first format, the couple with the fundamental class?
Yeah, that's yeah.
So it just says couple at the top.
Huh? Oh, yeah, sorry.
And on the left, it's also cup. What in the what's wait, what is what?
Yes, yes.
It's not just the concept,
Yes.
it's just the identity.
Yeah, this is just identity. So yeah, the whole point is, okay, use the project formula, you get this, which is, I mean, so this is this thing is the primary dual of this, right? Or shoot, what am I trying to say?
You're pushing forward the fundamental class of OSI bar inside.
Yeah, so that's
So-
which is the primary dual of.
You just wrote as without ice or star there.
Yeah. So if this makes sense, so this is this, right? And but this is literally, I mean, this is identity, right? And then this is just equal to what? So I P2 this Q2. Yeah, so this whole thing is just to saying that this operation is the same, I mean, this involving with this is the same as just oh, okay, sorry, I haven't proved the whole thing. This is equal to just Q2, sorry, intersecting with without pushing forward. So just cut product with this fundamental with this subfundamental group fundamental class is the same. It's just pull back and then push forward. Okay. Does that make sense? So pull back and then do this is the same. And it's the same as just pulling back and then push forward. I guess this is easier to see in just normal Thorell-Moore homology. But everything is fine in cohomology as well. Okay, and then what we need to do is we need to P1 push forward this thing. Whole thing. Right. So I guess I can just
No, you forgot I push forward. You just wrote I push forward to do pull back.
sorry.
Okay.
Well, I was trying to write down
I-
this.
Okay.
I mean, the last step is just using the Cartesian thing. So doing this convolution, P1, P2, A. Is this what I want to do right now?
Yeah, then I want to use what you just erased. That it's
Right, this is just equal to P1 push forward of and then P1, P2. Well, this should just be like this. Yeah. Wait, there's an I somewhere. Yes, sorry. Wait, this is just equal to Q1 push forward Q2. Okay. And now better Cartesian thing, this is just equal to should be should write down. I don't know, pi1, pi2. No, just pi as before, right? I guess I'll it's probably lost somewhere. Yeah, pi over there. This should just be equal to pi pull back. Pi push forward of there. Yeah, that basically. So this is exactly equal to E SI by definition before.
I have a question.
Yeah.
I guess, how come this is convolution?
Huh? Well, okay, so I mean, what we did is, so I have something like this is a class in here, right? Remember the convolution is you pull back a class here, and then you you do the transversal or like intersection with some class here, and then you push forward. That's what I wrote down.
It's not what's like in convolution, you have x cross x cross x, 2x cross x, 3x to x, and then you
Right.
models. So I guess it's so maybe you're right about G, so it's mod, so it's a module over convolution. So you use not algebra structure, but a module structure of h star gx over h star gx cos x, and yeah, because like at some point you should get just polynomials, and so maybe that's exactly what's happening. This h star g of x is just trivial thing, so it's just polynomials, and at some point you're just having fun with polynomials.
Yeah. So yeah, these are just operation on polynomials.
Yeah.
Yeah.
So when you say like Q2 pull Q1 push of A versus like I pull push I pull of A, like somehow at some point you had to use part one of that previous theorem, right? I mean that's the only place where I see you would.
So yeah, you need to use the fact that this is I mean the outside is a Cartesian square. Yeah. So you just
That's
use
just very
base change.
And the direction is still.
Yeah, so I think it should be G here. Yeah. I think this is yeah.
But then what you proved is not like DJ, but like something else. Because you don't use HT.
Right. Okay, I'll put a question mark here.
No, I guess it's yeah, maybe it's also G here, so that I mean this projection is G equivariant because you're doing stuff on the right and G x on the left. So I guess you are just doing stuff with polynomials. But when it's T's, okay, I'm not sure.
So HG, so H polynomial.
HG of G of B is HG of point, which is HC of point.
I mean, I'm scared to put G because all the Schubert cells are, I mean,
yeah,
they're not G equivariant, so.
yeah.
If you just want to like, check the
Yeah, if
So
So-
here this is something else than here.
yeah, let me just check real quick. I also don't know why they call this convolution, I guess. So the reference is equivariant cohomology in algebraic geometry, Anderson and Fulton. This is mostly in chapter 15 and 16, I think.
Yeah, I'll send it in.
Yeah.
Send notes and then notes, Fulton.
Yeah, I guess that they wait. Fine. Yes, sorry, I should have just gonna check the last thing. The reason, maybe the reason why they call convolution is if you have another thing, then you can define the action of the nil-Hecke algebra on that thing by convolution.
Yeah.
Yeah. Like if you have something that's you have G acting on X, then you get sort of the nil-Hecke algebra. Nil-Hecke. X on HT star of X by looking at you have, oh, why did I use, oh, whatever. By looking at this thing. Well, yeah, I mean, on here you will have it if you have Z G, then you can define Z convolving on so yeah, I guess we do want to look at the HT of G mod B because yeah, I guess that's where we started from beginning. That work.
Well, the group is the same everywhere, and there is no, we don't know anything about C equivariant for product G because, yeah, I guess at some point it comes.
When were we? I guess I'm confused because I think the confusion arises from.
I mean, first, if
Yeah.
we say DSI, it's not that DSI, but the map induced by DSI, then it makes sense.
Sorry.
And the convolution,
I mean-
that convolution is a convolution if we consider the convolution of the I and Q2 cross product with X or so.
Sorry, say it again.
Well, I think that convolution should be also a special case of convolution.
Yes.
X cross X, but the second part is like constant.
I guess I'm not sure what the convolution exactly.
Well, also maybe Anderson, Fulton, and Webster Senator are talking about like different things, and so there is discrepancy.
Yeah, I think that's the one I'm kind of
Whatever.
confused.
Also,
I think that should be something like convoluting with a kernel. And the convolution is the best generalization of that thing. I mean, for example,
Well-
an object can be considered as a kernel.
Wait, I mean, but in general, I mean, yeah, I think everything, I mean, the convolution structure should be on H G HG of G mod B. Right? I mean, because, I mean, this should come from. You just do the normal convolution. Just 3 of them. And then you have, yeah, I don't know, Pij. 1, 2. 1, 2. So. If you look at that way, then
that's.
then we, yeah, so we are doing T equivariant things. How?
Why is it?
Like, sorry, I mean, here. Correct?
Oh, T.
Because this is equal to Hg of. Yeah. D mod B cross D mod B. So I'm taking class here and then applying convolution with this class, which also live in this.
So the fundamental class.
Right.
Is a T equivariant.
The fundamental class is G equivariant, which is definitely T equivariant.
Yeah.
Well, no, sorry. So what I'm saying is like. So the nil-Hecke is defined, or the a priori, the first definition, they are operations on this thing, right? But this group is identified with this. So I'm saying that that operation on this is actually the same as convolving with some class here. And there is this thing does have a convolution structure, right?
But
I guess
you can't use T to. Translate.
Yeah, I think my proof is a little weird. It doesn't, maybe it doesn't work. Yeah, I think the confusion comes from there's a difference between, maybe difference between Anderson Felton and the yeah, Webster.
Yeah, well, I guess we should,
Yeah. I will try to figure this out and then send the correction to you.
yeah. No, let's make it.